this week's flipped classroom, we're going to talk about the angles of regular polygons. But before we start that, I've got a question here for you. It's going to be a theorem. We say, what is the interior angle measure sum of an n-sided shape? Okay, so if we look at a three-sided shape, we know that's the triangle, and that three sides has 180 degrees as its total interior angle sum. Probably take a guess about the four sides, 360 degrees. It works for squares, rectangles, but we haven't proven that very rigorously, so that's why I put a note there of how do we know that it's going to be exactly 360 degrees every single time. How about five sides? Anybody know what five sides interior angle sum is? We haven't dealt with pentagons at all, so I wouldn't expect anybody to. And so, of course, the question becomes, for n sides, is there a pattern or a formula? And how do we know if that holds true for very large numbers? You remember the last time, the way we tackled the theorem regarding the interior angle sum for a triangle, we connected the opposite, the point opposite the line here with a parallel line, and then we used the alternate interior angles theorem to prove that each one of these angles equals 180 degrees. Well, it turns out for the other ones, it's going to be a little bit easier than that. So for quadrilaterals, it becomes a little bit easier. We don't have to necessarily draw any parallel lines. But what we can do, no matter what the type of quadrilateral it is, we can always connect opposite vertices, right? So you imagine I draw that line, and it works for any type of quadrilateral, not just, in this case, a trapezoid. Okay, so we have two triangles. They're not necessarily congruent, but we do know that they each have three angles, and each of those three angles add up to 180 degrees. Okay, so here's where the math comes in. If we add these two equations together, the left-hand side keeping here, we end up with 1 plus 2 plus 3 plus 4 plus 5 plus 6 is equal to the sum of the right-hand side, which is 180 plus 180, and that's 360. So this proof works for any type of quadrilateral. You can always connect opposite vertices in a quadrilateral. That's the first postulate. So we're allowed to do that, and either way, no matter how you break it down, you're going to have these three. And the other thing you need to keep in mind is that 1 and 6 and 2 and 4 together, and 3 and 5 together, those are the angles of the quadrilateral. We can repeat this process as much as we want for any type of shape. So we just kind of show you what this recursive process is. I'm going to go ahead and draw this line in here, and look at that. We've got a triangle, and then we've got a quadrilateral. Well, we know about triangles, and we know about quadrilaterals now. And so if we just keep doing the same process every time, we'll be able to just keep drawing more triangles and then the previous one, right? So a pentagon's angle measure sum to 540 degrees. In other words, the way we get to an n-sided polygon, take the n-1 sided polygon, add another triangle to it. So each time we go up, we're adding another 180 degrees or another triangle. So, what about a dodecagon? Well, I don't really want to sit here and figure out the 11th, in which case I would have to figure out the 10th, in which case I'd have to figure out the 9th, and go through a recursive process. We don't want to do a recursive formula. We want an explicit formula. We want to jump right to the equation for a dodecagon. So, how many triangles does this dodecagon have? That's the key to this question, because if we're looking at this in terms of how many triangles they have, and an explicit formula starts to emerge. Okay, so here we have one triangle. Okay, here we have two triangles, and here we have three triangles. And go ahead and take the minimum number of triangles that you can draw that would divvy up the whole thing. I know you can do this where you can have more than these triangles, but the minimum number is what you're going to want to do. So we've got our three sides, four sides, five sides. Okay. Notice how many triangles they have based on the number of sides they have. Hopefully you notice that they have two less than the number of sides that they have. Okay, and of course we're seeing a pattern that, okay, for one triangle it's 180, for two triangles it's 360, and three triangles it's 540. Not a dodecagon? Well, we know that a dodecagon has 12 sides, and the pattern before that you were noticing was you take 2 minus the number of sides gives you the number of triangles that it has. Okay. In that case, we do 10 times 180 degrees for each triangle is 1,800 degrees. Okay, so can we extrapolate this and get a formula? Well, go ahead and take n sides. That means there's going to be n minus 2 triangles. And so to get the angle sum of those triangles, you do 180 degrees times the n minus 2. And that's how it will work. For any sided polygon, all you do is take the number of sides, plug it into this formula, subtract 2, multiply by 180, and you have their total angle sum. Let's go ahead and try it with this ugly looking heptagon here. A heptagon is 7-sided. Notice that this is not necessarily a regular shape. It could be any, as long as it's a convex, normal looking polygon here, it will work. Okay, so it's a 7-sided heptagon, so we plug in 7 into our equation, and we'll notice that it's a nice round 900 degrees is what each of these angles add up to be. So it gets a little bit more exciting when we talk about a polygon being regular, because then we can start talking about each individual angle. So remember that regular means it's both equilateral and equiangular. So if all of the angles are the same, then we can get each angle measure by taking the sum and dividing it by the number of sides. Let's do an example real quick. Okay, so we have an equilateral triangle, a regular triangle if you will, and we know each of its angles are going to be the same. So we take our total number divided by the number of sides that we have, or the number of angles, it doesn't really matter. Okay, and we take 180 is our total, divide it by 3 equal parts. Each angle is 60 degrees, but we knew that, of course. Okay, we could probably even know the square, the regular quadrilateral, right? You have the total is 360. There are 4 sides, so 360 divided by 4 is 90 degrees. Again, you should know that one. But what about a pentagon? You probably haven't thought about what each angle measure of a pentagon is, a regular pentagon. So then we have 540 is our total, divided by the 5 for the number of angles. So that each angle of a regular pentagon is 108 degrees. So here's our formula. You notice we have total angle sum divided by the number of angles or the number of sides. It doesn't really matter. Okay. Remember that the total angle sum was 180 times the n minus 2 degrees. Okay. So that means we just take our total and divide it by the number of sides, which is n. So it's a really easy adjustment. So let's return back to our heptagon, but this time let's make it a regular heptagon. Okay. So if we have our total divided by the number we have, okay, so we have 180 times 7, remember 7 comes from the number of sides, minus 2, divided by, this time, 7. In other words, remember before we got 900 degrees, it was a nice round number. 900 divided by 7 is 128.57 degrees roughly. Okay, so next time we will find out about how these angles help us find the area of the regular polygon. Stay posted.